This is the 5th lecture in our unit on algebraic foundations, square roots. We're going to kind of continue where we left off with exponents, except this is a little bit backwards. Before, let's just say we were asked to find a square. Say we were asked to find 5 square. In other words, if we had a square who has sides that are 5 on each side, we're asked, 5 square tells us the area, or how many square units are in the square. Well, in today's lecture, we're going to kind of do the opposite of that. We're going to find the square root. And the square root is the number used to multiply by itself. So in other words, if we're asked to find, we know that 5 squared is 25. If we're asked to find the square root of 25, that's going to be 5. And unfortunately for now, the only real way we have of figuring these out are memorizing them. And 5 is what we call a perfect square. And that is a number whose square is a whole number. In other words, the whole numbers, which we're going to learn in a little bit, 0, 1, 2, 3, 4, no fractional parts, no decimals, etc. So let's write down all the perfect square, all the perfect squares up to 10. So we know that 1 squared is 1, 2 squared is 4. What's 3 squared? This is the number. This is the number squared. 3 squared is 3 times 3, which is 9. 4 squared is 16. 5 squared is 5 times 5, which is 25. 6 squared is 36. 7 squared is 49. 8 squared is 64. 9 squared is 81. And 10 squared is 100. So if we're asked to find the square root of 49, we'd have to memorize that the square root of 49 is 7. For now. Well, later, much later in math, there's a way to do this without using a calculator and finding that, but it's a little bit out of our scope right now. But we're forgetting about a square too. And this symbol, let's say, look at the square root of 25. Well, we know that 5 times 5 is 25. But it's also true that negative 5 times negative 5 is 25. However, this symbol means give the principal root of 25. The principal root is the positive root. So the principal root is the positive root. Because it's also true that the square root of 25 is negative 25. However, this symbol we have defined, and a calculator will only give you positive 5. But it is possible to find the opposite of the square root of 25, and that's going to be negative 5. It is not possible to find the square root of a negative number, so square root of negative 25, because there's no number that you can multiply by itself that's negative and be positive. There's no real number. There's no real number that is negative that multiplies by itself to be positive, because a negative times a negative is a positive, not a negative. So there's no number that multiplies by itself to be negative. I'm sorry, negative. So there is a different kind of number that we're going to introduce in Algebra 2 that handles negative square roots. But for now, we're just going to stick with positive square roots. Okay, so let's find some examples here, some square roots. Let's find the square root of 64. And the opposite of the square root of 81. Okay, so for now, we're just going to have to use the chart that we've memorized. You could use the square root key on a calculator, but I'm going to assume that we're not using calculators right now. 64, we go through our squares, is 8 squared, so the square root of 64 is 8. The square root of negative 81 is negative. The square root of 81 is 9. Okay, the square roots that are not perfect. Square roots that are not perfect. For example, the square root of 12 is not perfect. Can only be approximated. They can only be estimated. When you type in the square root of 12 on a calculator and you get the digits that come out, that result is rounded to however much that calculator can handle. Because the square root of 12 in decimal form never terminates. It repeats forever. It doesn't repeat, it just continues forever, and it does not repeat. It does not repeat the same numbers. For example, we did a lecture, we said that 1/3 is 0.3333333, and it repeats infinitely forever. Or we said that 1/11 is 0.09 with a bar over it, because 0.9 repeats forever and ever and ever. Well, let's look. Let me bring up the square root of 12 here. Let me type up the square root of 12, an approximation of the square root of 12, so that we can see what we're talking about here. And I'm just going to type 12 on a calculator and hit square root. And that will tell me the square root of 12. So square root 12 is, okay, approximately, the square root of 12 is approximately 3.46410161514, and then other calculators go even more in depth than this, and they continue forever and ever and ever. And the calculation of these are actually done in calculus. Later towards the end of calculus, we can actually find these decimal numbers. But for now, we're just going to estimate. Okay, so here's an example. Suppose we go to the store and buy seeds to plant flowers. And one package of seed One package of seed covers 20 square feet. Okay, so if we plant a square garden, what is the dimensions of what is its dimensions? In other words, it's going to be a square garden like this. But instead of giving the side, we're given the area. Oh, 20 square feet. So we have 20 square feet in there. So what is this and what is this? Okay, so to figure this out, we're going to approximate the square root on a line here. Okay, so the top is going to be the square and the bottom is going to be x. And we're going to draw this out like this. So if we go through the squares, we know that 5 squared is 25, so that's too high. And we know that 4 squared is 16. So somewhere in here, this is 4 squared and this is 5. So we're looking for x. This is x squared. I did it backwards. Okay, that's fine. Okay, so I want to know what the square root of 20 is. So it's probably going to be closer to 4, but we're going to approximate by finding some of these square roots, and we're only going to approximate to 2 digits. We're going to round it to 2 digits. Well, I mean 1 digit, 1/10th place. Okay, so then we'd have 4.1 in here, 4.2, 4.3, and we'll see where 20 lies. So if we do 4.3 squared, that's 4.3 times 4.3. We want to see if that, see where it is on this scale, if we're higher than 20 or not. This is 129, right? And then that's a 217. So this looks like it's going to be 18.29. So we can say that 4.3 is 18.29. So we're still a little bit slow. Let's see what 4.4 squared is. And this one's not too bad because it's all 4s. Let's see, that's 176. Is 44 times 4. So that's going to still be a little shy. 19.36 is 4.4. Let's see what the square root of, let's see what 45 squared is. I already know what 45 squared is. And you can do the math here on multiplying by yourself. There's a trick to squaring numbers that end in 5. And this is 20. Oh, that's not 45 twice. Let me try that again. This is 45 times 5, which is 225, and 180, which would be 2025. So it's a little closer to 20.25 than it is to 19.36. So I would say that the dimensions should be 4.5 feet long. Finding these square roots by these approximations is something that you need to practice a little bit. It's more important to know that it's between the 4 and 5. But if you want to have an exact plot, it gets a little, it's better to get a little closer by hand here. Okay, so now we have a new kind of number that is real. It's still a real number. Because we talked about rational numbers, we've talked about whole numbers. Let's look and see all the different kinds of numbers we have. Okay. So we start with the natural numbers. And these are the numbers we use to count with. Okay. They come natural. And we use the letter N to kind of name the natural numbers instead of writing out natural numbers. And these are 0. Oh, well, you don't count with 0. You count with 1, 2, 3, 4, and so on. Okay. So if we had a diagram here, we'd have the natural numbers here. The next one is whole numbers. Whole numbers, and those are the natural numbers and 0, and they are represented by the W. So it's the same thing. It's going to be 1, 2, 3, 4, except we add 0 on the end. So this is the next set here. It's W, and then we introduced. Actually, I think we did rational numbers first, but the order of things is to do the integers next. And the integers are whole numbers and their opposites. And we represent the whole numbers with the script letters, the integers with the script letter Z. Because Z in German means integer, whatever word. That's why the Z. That's where the Z comes from. If anyone cares to know that, so they start. So it's 4 and -4, 3 and -3, 2 and -2, but they go all the way to negative infinity. Okay, and that's on this side too. We're just going. These are a little bigger, so we'll write them as Z. And then we have rational numbers. And that's got that word ratio in them. Ratio. Ratio means to divide. So it's the quotient of two integers. And we write this as P over Q. Where Q, and we learned in the last lecture that Q can't be 0. Or lecture before that. Q can't be 0. So these are also over here. And now we have, another thing about these is the decimal form. When we divide these out, like we knew that 1/2 is equal to 0.5. So in decimal form, the decimal terminates or repeats. It either terminates like this or 1/3, which was 0.3 bar. So next we have irrational numbers. These numbers never terminate nor repeat. They do the same. Forever, there's always a different number that comes out in a pattern, and it never repeats. Examples of this: pi. People memorize digits of pi. Pi never stops, and it never repeats the same number. And non-perfect square roots. For example, the square root of 3, the square root of 12, the square root of 20, which we found in the previous example, 20. Kind of approximation of it. And you're going to learn later about a number called E. It is also irrational. And it comes over here by itself. And we use the letter I to represent the irrational numbers. So why did I put all these together? Because all of these types of numbers are real numbers. Okay. The natural numbers are kind of in their own little thing here. But every natural number is also a whole number. So we can include that together. And all the whole numbers are in the integers too. So we can do that. And it just so happens that all the rational numbers, all the integers are rational numbers too. So we can kind of, okay. For example, -4/1 is a rational number. It's a quotient of two integers, but it's also -4. So it's an integer and a... So -4 is a rational number, and it's an integer. But it's not a whole number. Not all the integers are whole numbers. That's why it's not in that circle. But all the whole numbers are integers. And these two types of numbers, rational and irrational, make up the real numbers. So let's look at an example, and we're going to classify these numbers as best as we can according to this chart here. So classify, and the first one we're going to look at is 7/8. Okay. So we can say, and we're going to use the symbols. I'm not going to write everything out. If you want to write it all out, that's fine. We could say 7/8 is or belongs to, well, it's a fraction, so it's going to be a rational number. It's not an integer. It's not any of this, but it's also a real number, which we use the letter R for. What about 18? 18's got a lot. 18 belongs to the natural numbers, the whole numbers, the integers, the rational numbers, and the real numbers. So we can write this all out. Or you could say 18 is a natural number and write it all out like that. Or you can use this little symbol here. And what is the square root of 20 from our example? The square root of 20 is an irrational number and a real number. Okay, that's going to conclude the lecture on square roots. The next lecture is going to go a little bit different direction, and we're going to talk about the order of operations. I look forward to seeing you then. Until then, good studying.